Okay, hybridization. Okay, so hybridization, as you learned before in 3201, so you have sp3, you have sp2, and then you have sp. Okay, so I give you an example, just very simple compound. Yeah. Okay, so let's say, okay, so I have this compound here. Okay, let's say I put here CH3, H, H, and H. Okay, so I want to show you, okay, the hybridization of your carbon. Okay, different, okay, based on the type of covalent bond. Either you have single, double, or triple. Okay, this is the first structure. Okay, so and then I have other structure. Let's say it look like this. Okay, H, H. Okay, so I think I need to move it a bit. Make it slightly smaller. Okay, go down here. Okay, so and then the other one is, okay, so the left one, all carbon single bond. The second structure here, you can see carbon-carbon double bond. And then, of course, the last structure, what I want to draw here is carbon-carbon triple bond. Okay. Now, we want to talk about carbon ion, the stability, okay, based on the hybridization. Okay, so let's say, I circle the acidic proton attached to your carbon. So let's say first structure, that's the acidic proton, because you only have 2 carbon lah, and both carbon connected to 3 hydrogen atom. Okay. Okay, so the second structure, okay, we're talking about this acidic proton. And then the last structure on your right, I talk about that acidic proton. Okay. Okay, now, if you refer to this acidic proton, of course, when you react it with base, base will extract this acidic proton. So what you will get carbon ion. Okay, so you will get carbon ion. So I draw the structure of carbon ion, yeah, down here. So CH3, C, okay, so what you have here, H, your carbon ion. After base abstract your acidic proton. So the middle structure, so you have CH, carbon ion there. And then the last structure, you have carbon ion there. Okay. So whatever it is, when you look to this structure, the left structure, your proton, okay, bonded to this carbon. This carbon, all single bond. So, of course, the hybridization is sp3. The middle structure, you have this proton bonded to this carbon. You see my cursor. This carbon, you can see double bond there. So, this is sp2 hybridized, okay. So, and then the last structure, your proton here bonded to this carbon. You can see triple bond there, okay. So this one is sp. Okay. So now in terms of the hybridization, okay, so what we want to check is the S character for each hybridization. Okay. So if you look to here, okay, if I put it in the bracket, okay, this one is S character, yeah. If you refer to sp, so the S character is 50%. The P character is 50%. Yeah. Okay, so I just put in the bracket, it look like this, yeah, 50%, meaning your S character. Okay, so if you refer to sp2, okay, so you have 3 orbital there, 1 S, 2 orbital P here. So you divide 100 divided by 3 more or less. So you will get 33% of S character. Yeah. So and then for sp3, it's around 25%, your S character. Okay. Okay, so what you see here, okay, based on this, okay, if I draw, okay, the arrow from the left to the right, okay, so let's say I draw it like this, from the left to the right. So what you see from sp3 to sp2 and then to sp hybridization, the S character increases. Okay, in simple way, I can say like that lah. Yeah? So I draw a proper arrow. Okay. So move to the right. Okay, from sp3 to sp. So I can put here S character. Okay, I just draw arrow like this, yeah? Increases. Or you can say in your own word, okay? S character, okay? More for SP compared to SP2 and SP3 or something like that. I don't know. You just write your own sentence, okay? This is just a point, okay? So more from the left to the right, from SP3 to SP hybridization. So we can see the S character increases because SP3 only have 25% S character. Move to SP, so you will have 50% S character. Okay, so everybody know, right? S orbital, the shape is spherical, meaning your nucleus. Okay, your electron for orbital S, your electron, because the shape is spherical, so your electron very, very close to the nucleus. Okay, so what I can say here, okay, what point? Electron more close to nucleus. Okay, because if you compare S with P, S spherical shape. So spherical, so it surrounds the nucleus. Nucleus in the middle. So your electron density also very close to your nucleus. If you have P orbital, the shape is dumbbell. Okay, you have two lobes, right? Okay, so distribution of electron slightly far from the nucleus. Okay, so that's why you have S character. It's make electron more close to your nucleus. Meaning, when your electron more close to the nucleus, your carbon ion, it will stabilize. Okay, because your carbon ion here is carbon negative charge. Okay, so the nucleus, okay, you see my cursor, because each carbon ion negative charge. Okay, so you have extra electron belong to each carbon here. Okay, so that electron close to the nucleus. In other words, it will stabilize your carbon ion. Okay, so I put here in the bracket stabilize. And it will stabilize your carbon negative charge, or it will stabilize the carbon ion. So when it stabilizes, so of course, the stability of your carbon ion increases as well. Okay, carbon ion, yeah, increases. When the stability of carbon ion increases, automatically acidity of the proton, okay, increases as well. Okay, so that's the explanation for the first factor. Okay, so the first factor is hybridization. Okay, the keyword here, increase the S character will make the electron more close to the nucleus, and it will stabilize your carbon negative charge. When it stabilizes, automatically the stability of carbon ion increase, and it will make acidity of your proton, the one that I highlight in green color, also increase. So that's why when you compare this acidic proton, yeah, okay, the one that bonded to carbon triple bond, the pKa value is lower compared to this proton that bonded to carbon double bond, compared to this proton bonded to carbon single bond. Okay, so you can check. Okay, if you refer to this, yeah. Okay, so let's say I give you the pKa value for this proton is around 50. So very low, the pKa value. Okay, very high, sorry, very high the pKa value, which is around 50. Okay, so pKa value high, meaning it less acidic. Okay, that's the relationship you should know. Okay, okay, so here the first factor. Okay, we done with that. Okay, we move to the second factor. Okay, so the second factor is inductive effect. Okay, we already talked a bit about this related effect because it's related to the EDG and EWG group. Okay, so I just want to give you an example like this. Okay, so let's say I have this structure here. Okay, for the explanation. Okay, straight away I draw it like that. Okay, this one you already abstract the proton using base. I straight away draw the structure of carbon ion. Okay, so and then I can have other structure. Let's say so structure like this. Okay, and then I can have other structure as well. Let's say CH3H like that. Okay, and then I can have another structure CH3, okay, and then up here CH3 and then minus. Okay, so I can have structure like this. Okay, this is for carbon ion. Okay, what you see here, you can see the difference in terms of the structure. The first carbon ion on your left, carbon bonded all 3 hydrogen atoms. The second structure from the left, you can see 1 hydrogen replaced with this methyl group. Move to this structure number 3 from your left, so you replace 2 hydrogen with this methyl group. The last structure on your right, now we try to replace all hydrogen with 3 methyl group. Okay, so what you see here, carbon ion is like carbocation. Okay, you can say about the class of your carbon ion as well. Okay, if you look to here, okay, we can label it here. This is methyl carbon ion. So you have CH3 minus, so methyl carbon ion. So the second structure here, so because this carbon ion bonded to only 1 alkyl group, this is primary carbon ion. So the third structure here, so this carbon ion bonded to 2 alkyl groups. So this is secondary class of carbon ion. Okay, so and then the last structure is tertiary class. Okay, it's same like carbocation. Okay, the definition or the classification. Okay, either primary, secondary, or tertiary. Okay, but what I want to highlight here in terms of inductive effect. Okay, now what you see here, your methyl. Okay, if I circle it using yellow color, you have that methyl group, you have that methyl group, you have this methyl group. Okay, you should know by now because you already see this group. Methyl is EDG group, right? EDG group. Okay, so now if you refer to this, EDG group donate electron. Okay, so now the donation of electron through sigma bond. So that's why we call it inductive effect. Okay, so it's donate electron through sigma bond like that. Okay, if you draw, it is arrow on the bond. Okay, it's look like that. Okay, this is donation through sigma bond. Okay, so that's the first thing you need to know. Okay, so and then based on that, okay, so I can draw arrow like this, okay, for the explanation. Okay, move from the left to the right. Okay, so you can see different class of carbon ion. Okay, based on this structure of carbon ion, what you can say there, okay, the electron donating group increases. I just draw like that. This is a point. Okay, from the left to the right, you can see the number of EDG increases. From the left, 0 EDG. Go to the second structure, you have 1 EDG group. Go to the last structure on your right, you can see 3 EDG groups. Okay, So from left to the right, EDG group increases. So everybody know, okay? So what EDG do? So EDG donate electron to your carbon ion, okay? So donate electron to carbon ion or carbon negative charge, meaning your carbon ion already negative charge. It's already rich with electron. When you have EDG, EDG donate electron to your carbon ion, it will destabilize your carbon ion. Why? Because your carbon ion now very, very, very rich with electron. Okay? So donate electron to carbon ion, okay? It destabilize your carbon ion. Okay, destabilize your carbon ion. In other words, when this EDG destabilize your carbon ion, so the stability itself will be decreases. Okay, related to the stability, automatically acidity of proton also decreases. Okay, so meaning the proton, if we refer to the same color like before, okay, so this proton, I mean the proton that you abstract, okay, so because I didn't show it, yeah, okay, so the proton attach here, the proton attach here, the proton attach here, and the proton attach here, okay, so the acidity of that proton also decreases, okay, so that's the explanation in terms of stability if we talk about inductive effect. Okay, this one is an example for EDG. Okay, so you can do for EWG as well. You can try by yourself. Okay, so I just want to show you other example. Okay, related to this inductive. I just want you to compare these two structure here. So let's say you have this carbon ion. So you have CH3, HH. I want to compare it, okay, with this compound here, NO2. Okay, you have these two structures. Okay, so we want to talk about inductive effect. Okay, so the first structure here, okay, so if I highlight it again, so you can see this methyl group. Methyl group here is EDG group. This one is EDG. On the other hand, okay, so I have the right structure. The right structure, I have NO2 group. Okay, NO2 group. This one. NO2 group, okay, so by now you should know already lah, yeah. Okay, NO2 group is EWG group. Okay, so now, previous example I show you, okay, only in terms of EDG. Now, I want to compare if you have EDG and EWG. Okay, okay, so as I said before, okay, so the left structure, if you have EDG, EDG will donate electron to your carbon ion. Okay, so through inductive effect. Okay, you draw the arrow on the bond. Okay, it's donate electron through sigma bond to your carbon negative charge. When this methyl EDG donate electron to your carbon negative charge, it will destabilize, okay, your carbon ion. Why destabilize? Okay, destabilize, okay, the carbon ion. Why? Because your carbon negative charge already rich with electron. Now you have EDG. EDG donate electron to your carbon that already rich with electron. So this carbon, so high yeah, density of electron. So it will destabilize. Okay. So on the other hand, if you look the structure on your right, so your carbon ion, okay, rich with electron already. Okay. But you have this NO2 group, which is EWG group. EWG group will pull electron from your carbon ion. So You draw the arrow like that on the bond. NO2 pull electron from the carbon ion. So meaning when your EWG NO2 group pull electron from the carbon ion, it will stabilize your carbon ion. Okay, it will stabilize. Okay, your carbon ion. Yeah. So from there, when it is destabilized carbon ion, so it's related to the stability. So stability will decrease. In other words, acidity of the proton also decrease. Yeah. Acidity here, I'm referring to the acidity of proton. Which proton? Proton that already abstract from this carbon ion, yeah? Because I straight away draw the structure of carbon ion. So you should know, so before you form this carbon ion, you have proton here, right? You have base abstract that proton, then you get this carbon ion. So that proton that you abstract, so this the acidity for that proton, yeah? Okay, on the other hand, if you have EWG group, it stabilizes the carbon ion, meaning stability of your carbon ion also increase and your acidity of the proton that abstract by the base also increase. Okay, so that's the explanation. Okay, for the inductive effect, depends either you have EDG or EWG. Okay? Okay, so as I said, you can do by yourself. Okay, the comparison for all structure containing EWG group. You can explain. Okay? Okay, so that's the second inductive. Okay? So, and then the third inductive, the third factor influence, okay, the stability of your carbon ion. Okay, so I write it here, the third one, resonance effect. Yeah. Before this, inductive effect. Inductive effect, okay, so either you have EDG or EWG, donate or withdraw electron through sigma bond. Okay, the third factor is resonance effect. Okay, everybody should know. When we talk about resonance, it's related to the conjugated system and it's related to the delocalization of electron. Okay. Okay, now I want to give you an example like this. Okay, so let's say I have this structure here. Okay. I straight away draw the carbon ion, yeah? But you should know lah, yeah, actually that carbon ion, okay? So you have this proton, yeah? Okay, so it looks like that. So actually, when we talk about the acidity of the proton, actually this proton, okay, the properties, the acid properties of this proton, yeah? Okay, because the previous example, I didn't show you. For the second factor, I didn't show you this one. I straight away draw the structure of carbon ion, okay? So, but you should know how that carbon ion form, yeah? Okay, so that's the first carbon ion, for example, for this discussion. Okay, and then I have other structure. So let's say I have something like this. Okay, and then maybe I have structure like this. Okay. Okay, so you have these three carbon ion. Now you want to talk about their stability. Okay, and you want to explain it in terms of resonance effect. Okay, so you compare all these three carbon ion structure. Okay, if you look to the first structure on your left, you see this carbon negative charge. So if you check your structure, go to the left, you see two single bond. So you cannot see any conjugated system there. If you go to the right, same thing, you have these two single bond, no conjugated system. So meaning this reaction, no resonance. Okay, this structure, no resonance. Why? Because you don't have conjugated system, okay, in your structure. So the middle structure here, if you go to the left, negative charge, single, single. Again, no conjugated system on the left. But if you go to the right, you have negative charge, single, double. So you see this is the conjugated system in the structure. Meaning, if you have this conjugated system, you can draw resonance form for it. Okay. So if you draw it, it look like that. Okay. So resonance form, okay, I'm using blue color. So you have that like that. Okay. You have that conjugated system and you can delocalize electron. The structure on your right, okay, so you have the center carbon ion. If you go to the left, negative charge, single, double, you can have conjugated system on the left, and then you can have conjugated system on your right as well. So meaning, okay, you can have, okay, resonance form for this. Yeah. So let's say you go to the left, what you will get? You will get structure like this. Okay. If you go to the right, okay, if I'm using a different color of arrow, so it's look like that. Okay. So what you will get something like this. Okay. You see? Okay. So resonance effects is related to the conjugated system and electron delocalization. Okay. Based on that, okay. So maybe I erase this one lah, yeah. Okay. So you should know. Okay. Okay. Based on that, so I can discuss in terms of the stability of this carbon ion. Okay. If I draw the arrow from the left to the right, what you see here, okay, this is just a point. You need to write using your own sentence, yeah? If you look to that tree structure from the left to the right, okay, in simple way, conjugated increases. Meaning conjugated system increases lah, yeah, in your structure. Structure on your left, no conjugated system at all. So structure in the middle, you have some, okay, part of the structure with conjugated system, and then the structure on your right, fully conjugated system. Okay, so left to the right, conjugated system increases in the structure, meaning when you have conjugated system, if you have more conjugated system, meaning more electron delocalization. How I can write it? Electron delocalization increases as well. So I just write it like that. Yeah, electron delocalization increases as well. Okay. So when you have more conjugated system, more electron delocalization, in other way, you will have more resonance form. Okay, so maybe you can put it in the bracket, more resonant form or more resonant structure. Okay. Okay, so as you learned before, more resonant structure meaning more stable. Okay, your structure. So here, the stability of your carbon ion will increases, and automatically the acidity of the proton, remember, okay, increases as well. Okay, stability is stability of your carbon ion, yeah. Okay, same thing, the other two factors. When I talk about the stability here, it's referring to the stability of your carbon ion. When we talk about the acidity, we're referring to the acidity of the proton that abstract by the base, okay, to form this carbon ion. Okay, okay, so this is the resonance effect. Okay, okay, more resonance form meaning more stable your structure. So in other words, your carbon ion is more stable. And if you relate with the acidic proton, so the properties of acidity also increase. Okay. Okay, so that one example. Okay, so I have another example. Okay, for this resonance form. Okay, let's say you have this structure here. Okay, so this is the carbon ion. As I said, before you form this carbon ion, you have proton here, right? The acidic proton. You have base abstract that acidic proton, okay, cleave the bond, give electron to this carbon. So that's why you have this carbon ion, okay? Okay, so I want to compare the left structure with this structure here. Okay, so I want to compare these two structures. Okay, okay, now what you see? The left structure, okay, so you have negative charge, single, double. So of course you can see conjugated system there. The right structure, you have negative charge, single, double. You have conjugated system there. Yeah. So, but if you compare these two structure, the right fragment for the left structure, you only have methyl group. For the second structure on your right, okay, the right fragment here you have, let's say, if you base on this structure, you have methoxy group. Okay, so everybody should know oxygen here. Okay, you have a lone pair, right? Belong to this oxygen. You have two pairs. Okay, so if you draw it, it look like this lah. Actually, need for me to draw it. You should know. Okay. So as I said, on the left side, you have conjugated system. On your right also, what you see here, you have lone pair, single, double. You have another conjugated system on your right. Okay. Okay, so now for this example, okay, so if I compare these two structures here, okay, so I draw the arrow. Okay, I think I just bring it down here. Okay, more easy. Okay, okay, so I can draw the arrow. Okay, so let's say for the explanation. Yeah. So this is using arrow lah. Yeah, of course, in the final exam later on, if you ask question like this, okay, asking you to discuss, okay, so maybe you can label it, okay, 1, 2, or A, B, doesn't matter, okay. So this is, I just use arrow, left from the left, move from the left to the right, okay. Okay, so if you compare these two structure, okay, what I want to highlight here, conjugated increase, right? From the left to the right. Because structure on your left, only one side. Structure on your right, you have two sides of the conjugated system. Here, left side and right hand side conjugated system. So meaning, if you have more conjugated system, so it will form more resonance form. Yeah, more resonance form. Okay, like before lah, yeah, like before. Okay, so you can draw if you want, okay, you can draw it. So resonance form is look like that. So what you will get double bond, O minus, it's look like that. Okay, so this one, same thing. If you do the resonance form for the left fragment, so you have this one, like that. Okay, if you have the right hand side, okay, so you have lone pair, donate to here, go to there. The blue resonance form, you have O minus, double bond O plus. Okay, so of course, increase number of the conjugated system from the left to the right, it will increase number of resonance form. Okay, so that's the relationship 0.1 and 0.2. Okay, unfortunately, okay, yes, okay, if you look structure on the right, so you have more resonance form. Yeah, okay, more resonance form. If you refer to the basic, more resonance form, meaning more stable. But this one oppositely, okay, the structure on your right, even though it has more resonance form, but it is less stable. Why? Now you have competition. Yeah? Okay, so your carbon ion, carbon negative charge, form a resonance form with this oxygen at the top. Okay? On the other hand, your oxygen on your right here, you have lone pair, and that lone pair also can use for the resonance form. So now it's compete between this carbon ion and this oxygen for the resonance form. So more resonance form, but okay, you need to have here competition of electron distribution, okay, by oxygen atom. Okay, you have competition for the structure on your right. Okay, so competition between your carbon negative charge and oxygen with lone pair. They compete, okay, to form a resonance structure. So when you have this competition, it will stabilize, it will destabilize. Okay, destabilize carbon ion. So in other words, when it destabilizes, the stability of your carbon ion decreases and the acidity of the proton also decreases. Okay? Okay, so that's the resonance effect. Don't confuse, yeah? Okay? Even though structure on the right, more resonance form. Normally, more resonance form, more stable, right? For this one, no. Okay, because you have competition. Okay, you can compare. Okay, if I go back to here, okay, what is the difference this structure on your right with the structure this one? Both, okay, have more resonance form. Okay, but why this structure down here less stable? Why structure up here is more stable? Yeah, because this structure here, up here, okay, you can see this carbon ion, no competition for the delocalization. The delocalization of electron only use electron from your carbon ion, either to the left or either to the right. No competition. The delocalization only involve electron from your carbon ion. But this time, the delocalization compete between carbon negative charge, which is this carbon, want to donate electron here. At the same time, you have oxygen with lone pair. This oxygen also want to move electron to here. So they compete to each other. So make the stability decrease for this case. Okay? So that's the explanation. Can you follow, student?
Yes, Doctor.
Okay. Okay, so that's the stability. We done, yeah? All the three factors. Yeah? Okay, now we go back to our slide up here. Okay, so we're done with this one. And then, okay, we go to the reaction for enolate, or other word for carbon ion. Okay, because carbon ion and enolate is resonant to each other. Okay. Okay, so the first reaction, okay, so this one, alkylation reaction. This one, I don't want to repeat it again because you already see it under stereochemistry topic. Okay, so actually this one, if I want to write in full, it is alpha alkylation. Yeah, alpha alkylation reaction. Check stereo topic. The one that related to the kinetic and thermodynamic. I already discussed the mechanism there as well. Okay, so by this time, no need. This time at this topic, you just need to know the mechanism. Yeah, the kinetic and thermodynamic for the previous topic, the stereo topic. So you can take the mechanism. Okay, you can bring it here. You can write it back lah here. Yeah. Okay, so this is just general equation. Okay, so what you see here, it is reaction between ketone, ester, or maybe nitrile. And actually here, okay, it also, okay, can use aldehyde. Yeah, aldehyde. Yeah, so you add there. Yeah, alpha alkylation, you can use aldehyde, ketone, ester, or nitrile. Yeah, as a starting material, and then it will react with your alkyl halide. Okay, so it's involved with two steps if you remember. Okay, LDA. Okay, you learned before it is kinetic. Okay, and then you have thermodynamic. You need to use small size of base. So this is just example, yeah, equation. So of course you can play around with the base. We can change the base. Okay, doesn't matter. It's not necessary LDA here. Okay. So my first equation here is ketone. Okay. So and then my second equation here is nitrile compound. Yeah. Whatever it is, okay, for this reaction, you must have acidic proton. Okay. You must have acidic proton that bonded to the carbon next to the C double bond O. You must have that one. Otherwise, you cannot produce enolate. Because remember, this is reaction for enolate. Yeah. Okay. So you must have proton that bonded to the carbon, and that carbon must next to the C double bond O. Okay. Like this one lah. Okay. Like this one, yeah. Okay. So let's say this one. So your C double bond O there. So the acidic proton actually it's here. Okay. So that one. H bonded to the carbon, and that carbon next to the C double bond O. Okay. So instead of C double bond O, you also can have this group here, nitrile group also. Okay. Because you can draw resonance structure lah, yeah, for this one as well. Like you can draw resonance structure for this. Okay. So this is your acidic proton here. You learn already, right? Cn is EWG. Why you have acidic proton here? Yeah. Okay. So you know. Okay. The explanation lah. Yeah? Okay. So this is the first reaction. Okay. So just go back to the stereo topic. Okay. Abstract the mechanism. Okay. And then you copy it back here. Okay. You can draw the mechanism using your own structure. You just play around. Yeah. Okay. So that's the first reaction. Yeah. Okay, what time now? Almost 12 o'clock. Okay, so we rest for a while, student, then we continue, yeah?
Okay, doctor.
Okay. Okay, so of course, okay, your ketone will react with this base. Okay, so of course that one will be happen. Okay, in the first step. Okay, I draw it. Okay, and then you have base Na plus OH minus. Okay, what you need to know? Okay, you have base on the arrow. You put base in your on bottom plus. So of course, base react with acid. So this is reaction for enolate. Enolate relate with the carbanion. So how you produce carbanion? You must extract acidic proton. How you can extract acidic proton? You need to use this. Okay, so that the basic. Okay, so of course, if you look to here, you have CH3 on the left, CH3 on the right. So these 3 hydrogen atom on your left and 3 hydrogen atom on your right are identical. So it doesn't matter you extract which hydrogen. It's come back to the same carbanion structure. So let's say I just draw like this. I need to show it because this is mechanism. You need to show electron flow, okay, using curve arrow. Okay, so that's why I need to show this one acidic proton. So what will be happen? As you learned before, formation of carbon ion, base abstract proton, okay, cleave the bond, give electron to the carbon. Okay, what you get there, you just draw. So you have this carbon negative charge, which is, we call it as a carbanion. Okay, remember, this is reaction for enolate. Okay, so you need to draw enolate form for this carbanion. Okay, enolate is resonance structure of your carbanion. So you must have this double-headed arrow. So for the enolate formation, you do electron delocalization. Oh, sorry, I should use pink color, yeah. Okay, so you do electron delocalization. So then you get this enolate structure. Okay, so this one is enolate. Yeah. So all the mechanism under this topic, you must show these two things. You must show formation of carbanion, and then you must show the enolate resonance of your carbanion. That one is compulsory. You must show it. Yeah. Okay, so and then after you produce carbanion enolate, then this will react with the second molecule of your ketone. So the first ketone already react with your base. Okay, that's the first molecule of ketone. Now, after you produce enolate, this enolate will react with the second ketone. Okay, because you have two molecules of ketone, right? Now I'm talking about identical ketone. As I said, you can use different ketone. So different ketone, ketone 1, ketone 2. Ketone 1 react with base, and then ketone 2 will react with the enolate. Okay, simply like that. Okay, so this one is react with second ketone. So your ketone is look like that. So what will be happen? Okay, so this one enolate. Okay, electron go back to there, use this double bond, attack your carbonyl carbon, cleave this bond, give electron to oxygen. Okay, so you just follow the mechanism. Okay, the electron movement, the electron flow, show it using curve arrow. Yeah. Okay, so what you get? What you get here? So now you combine, you connect these two structures. So the connection through carbon-carbon bond. Through which carbon? So if I highlight it, okay, through this carbon and that carbon. So you produce new carbon-carbon bond formation between them. The yellow color of carbon. So you draw it. Okay, if I draw it, okay, starting from the left structure here, your enolate. So I have that one. You get back your C double bond O, and then that carbon, yellow color, form a new bond with the other yellow color on my right. So, and then you have O minus, and then you have this. Okay, what is it? And then you have another methyl, yeah? Because, okay, if I highlight it using yellow color again, so for easy for you to follow, so you have this and this. Okay, that two carbon, yellow color now connected together. Okay, you produce that new bond between carbon. So carbon on my right here, so you have two methyl group, yeah? So you check your here, so you have one methyl and another methyl. Okay, okay, so this one. So and then the next step, okay, so because this is the first step, so the first step, you need to react it, okay, from this, yeah, from this, your base, yeah, from the first step, OH minus abstract proton, you get water, right? So you can use water here. Depends on the base, yeah. If you have a methoxide, okay, methoxide, connect with this hydrogen, you produce methanol. So you can use methanol here lah, depends, okay? Okay, so what will be happen next? because your product here from the first step must be beta hydroxy ketone. So what you see, this is already your ketone. Carbon next to C double bond, carbon alpha. Next to carbon alpha is carbon beta. So if we label it, this is carbon alpha, this is your carbon beta. So you must get hydroxy group attached to carbon beta. So how you can get the OH group there? Now you have O minus. So simply, this oxygen donate electron to the proton to form OH group. Okay, so this one, abstract proton, cleave this bond, give electron to O. So you get back your OH minus. Yeah. Okay, so you draw it. So double bond O, now OH. Okay, it's look like that. So this one, beta hydroxy ketone. Okay, beta hydroxy ketone. Okay, the product from the aldol reaction. Okay, so and then proceed with the second step. You have acid. Okay, so what will be happen here? Okay, we done with the first step, aldol reaction. Now we want to continue with the aldol condensation. Yeah. Okay, so aldol condensation, you have acid, yeah, HCl, and then you heat it lah, yeah. Okay, so what will be happen? Okay, so aldol condensation. Okay, so this case you will eliminate water for the condensation. So this one is already OH group. To eliminate it as a water, you can form a water fragment first. Okay, because OH minus, as you learned before, is not a good living group, right? Okay, you need to convert it to a good living group. So very simple for OH group. So you just convert it to the water. Okay, how you can form water fragment? So O there, you have lone pair. You donate it to this, you cleave that bond. So what you get, okay, I continue down here, yeah. Okay, continue down there. So what I get, this one, OH2 plus. Now clearly, this fragment here is water fragment. So now you can eliminate it easily from your structure. Okay, so what will be happen next? How you can eliminate, okay, that water fragment? Okay, because you want to produce alpha, beta, unsaturated. You must produce double bond. So how you can do it? Okay, so you have another acidic proton there. Remember, your carbonyl, your ketone, each carbon, okay, you have 3 hydrogen atom, right? Acidic proton. So you have here another 2 acidic proton. So you can react it with a base again. Okay, so this one, abstract that one, cleave this bond, like that. Yeah, so what you get? You get C double bond O, and then you get this double bond, and then you get structure like that. Yeah, so if you follow, okay, the label alpha, beta, alpha, beta. So this one is alpha, beta. So your end product here from the condensation, alpha, beta, unsaturated ketone. Okay, so this product. Okay, so your carbon, the bond formed between carbon-carbon, so actually this one lah. If you want to follow it. Okay, I circle it using yellow color. Okay, so that's the condensation reaction. Okay, okay, so very simple lah, also straightforward. Whatever it is, the keyword, okay, all the reaction, okay, here you must form carbon ion and then must form inlet first. Okay, and then the rest you just proceed, follow. Okay, okay, so this is the aldol condensation. So my example here is I'm using identical ketone. Okay, okay, normally, yeah, chemists, okay, don't like to use different carbonyl compound because we have a mixture of product, because we cannot control our reaction, yeah. Of course, from that mixture of different aldehyde or ketone, it will produce mixture of product. So very difficult for us, okay? And then later on, want to isolate which compound we want, yeah? Okay, so chemists prefer to use identical ketone or aldehyde. If you want, you also can do the mix, okay, structure, okay, just to make sure only one structure has acidic proton, the other structure don't have acidic proton. That one, you can get single product as well. Okay. Okay, so you can try lah, yeah. So mix, okay, different structure of ketone. What is the possible structure you get? Follow this mechanism, exactly the same. Yeah. Okay, and then reaction number 3. Okay, so we have here Michael reaction. Okay, this one is reaction between diketone, diester, or beta keto ester, and also ketonitrile. Okay, with alpha beta unsaturated carbonyl compound. Yeah, so this one totally two different things. Okay, you have two different compound. Let's say you have diketone, you react it with alpha beta unsaturated carbonyl compound. Okay, totally different two compound for the reaction. Okay, so whatever it is, okay, for this reaction, this one diketone, diester, the yellow color, yeah, ketoester or ketonitrile, the yellow one, it will act as a nucleophile in your reaction, because we use different structure, so you should know which one is nucleophile, which one is electrophile. If you use for aldol reaction like before, identical ketone, so doesn't matter lah. Okay, so because same, okay, identical structure of ketone. Okay, so this one, the yellow color will act as a nucleophile in this Michael reaction. And then the other one, alpha beta unsaturated carbonyl, it will act as a electrophile. Yeah, later on, okay, in this step. Yeah. Okay, so this is general equation. The example here. So the first blue color here on your left, this one is diketone compound. Okay, so this one is diketone. Diketone meaning you have ketone, two ketone in the structure. So clearly, okay, you can see two ketone there. Okay, so one here and another one here. Okay, so diketone. So the word beta, because of the position. Yeah, because of the position. Yeah, if you look to the position, the first ketone, okay, the first carbonyl group, carbon next to its alpha, and then carbon next to alpha is beta. So that's why the second ketone at position beta. So that's why we call it beta diketone. Okay. Okay, same with beta diester. You have two ester group in the structure. The second ester at position beta. Yeah. Okay, so this one, another reaction, diketone with, this is your alpha beta unsaturated carbonyl. Unsaturated carbonyl, it can be a ketone, it can be aldehyde, it can be ester, yeah, because ester contains C double bond O also. Okay, we can call it as a carbonyl compound as well. Yeah. So alpha beta, okay. So this is your carbonyl C double bond O. So here is alpha, here is beta. Okay, that's the other material involved in the Michael reaction, alpha beta unsaturated carbonyl. Carbonyl because of this C double bond O lah. Yeah. Okay, so again, reaction, okay, under a basic condition, because this is enolate reaction. Why you need to have base in your round bottom plus? Because you need that base to abstract proton to produce your carbanion. Okay, so that's why all the reaction here, we need base. Okay, so otherwise we cannot form our carbanion. Yeah. Okay, so below also the general structure. Okay, other example, let's say this one, you have beta ketonitrile. So this one, ketonitrile. Okay. So nitrile, this one, the nitrile. So alpha, beta ketonitrile. Okay. Okay, so you can use any base lah, basically here. Yeah. Okay, so that's the product lah. Yeah. Okay, so the product. So this is the new carbon-carbon bond formation. You see the connection between two molecules. Okay, so the first structure, so you have the blue compound connected to the black structure. Okay, through carbon-carbon bond formation. Okay, the below one, pink color connected to the black color of structure through here. Okay, through carbon-carbon bond formation. Okay. Okay, so the mechanism. Okay, so I think I just showed you this mechanism, and then the next one, Clayson. Okay, you try by yourself, yeah. Exactly the same concept, yeah. Okay, so only this one. Okay, for the Michael. So let's say I have this example. So we're using specific example for the discussion of the mechanism, yeah. Okay, so let's say I have this, what I want to use. Or maybe I use the second equation, this one. Okay, the second one. So I have that one. So, and then I have Cn. So I react it with, okay, so let's say I have something like this, COOCH3, ester, yeah? Yeah. So, and then this one, okay, let's say we use OME. Okay. So what is it? Okay, we want to talk about mechanism, this one. Okay, so that's the example. Okay, so this one is sodium methoxide, yeah, my base. OME, ME is CH3 group, methyl group. So methoxide ion is my base. Okay. So the mechanism, okay, as I said, this one, beta ketonitrile, this one is your nucleophile. Okay. Okay, so so to make it nucleophile, of course, okay, nucleophile now is your carbon ion, yeah, enolate. Okay, to make your carbon ion or enolate, you must react first this compound with base. Okay, so I draw the mechanism. Okay, so I have Cn, so I need to show this acidic proton. Okay, so you react it with OMe minus my base. So what will be happen? First, as I said, the important thing you need to show the formation of carbon ion and enolate. Your carbon ion is nucleophile. Okay, so that nucleophile come from this beta ketonitrile. Okay, so very common like before. So what you get, you just draw back. You get carbon ion there, Cn. Okay, so and then this one can have resonance form. Okay, what you see there. So you can form enolate. So what you get O minus, double bond there, and then Cn. This one is carbon ion. This one is enolate. Okay, so that must, okay, show for the mechanism. Okay, okay, so you produce this carbon ion enolate. So this is your nucleophile now. So this nucleophile will react with electrophile. Okay, so your electrophile, alpha, beta, unsaturated carbonyl compound. Okay, so this one, right? Okay, as we wrote it previously, this is electrophile, this is nucleophile. So your electrophile, the second compound, so you draw it here, okay, COOCH3. Okay, I just draw, go down there. Okay, so what will be happen? Mechanism like before, enolate. Okay, so you go there, this one, attack carbon beta. Remember, so this is carbon beta, yeah? Because this material is alpha beta unsaturated. So this is alpha, this is beta. So and then what else? Cleave the bond, give to the electron. So what you get? Okay, I draw to the left. Yeah. So starting from the top structure here, your enolate. Okay, I draw it back. Okay, you get back your C double bond O and then CN. Okay, and then you form a new bond between carbon. So, and then, okay, so if I highlight it, this carbon and that carbon, you connected it together, the yellow color. So that yellow and that yellow, okay, so what you get? So the other left side, you have 2 carbon. So 1, 2, and then right hand side, okay, 1, 1, 2 as well, COO, CH3. Now this is negative charge. Okay, so that one. So you follow, yeah? The new bond between carbon-carbon. Okay, I highlight it using yellow color. Yeah. Okay, so that one. So you get that one, yeah? Okay, so what will be happen next? Of course, your end structure must be neutral. Okay, you cannot stop there. Okay, you already react with base. Okay, you already react with the second molecule. Now you get this. You have carbon negative charge. So you need to neutralize it. Okay, so how you do it? So for the neutralization, so you react with, okay, what will be happen here? Your base methoxide ion abstract proton, right? It produce methanol. So you can use methanol there. MEOH, okay, for the neutralize of the negative charge on the carbon. So what will be happen? This abstract proton cleave this bond. You will get back your base methoxide ion. Yeah. So you draw it. So C double bond O, CN, this one, and that one, COO, CH3. Okay, finish. Okay, that's the mechanism. Okay, that's the carbon. Okay, so that's the mechanism. Yeah. Okay, done with this one. Any questions, student? Okay, so I proceed, yeah? Okay, so we done with the third reaction. Reaction number 4, we call it as a Claisen condensation as well. Okay, so this one is condensation, meaning, okay, for the condensation, you must eliminate or you must remove something from your structure. Okay, normal condensation, everybody know, okay? The simple compound you can eliminate is water, okay? But because this Claisen reaction, okay, you react ester compound. So in ester compound, you have OR group attached to your carbonyl. Okay. So what you will eliminate from the condensation here is alcohol. Okay. Alcohol. So what you see here, so this is actually your leaving group. Okay. Your LG leaving group for this reaction. Yeah. Okay. So that's why you can see here, if you look to this equation, this is general equation. Yeah. Okay, so what you see here, I have this one is ester, yeah, reaction between 2 molecules of ester. So you can have red color of ester react with blue color of ester. Undergo this Claisen condensation. So you connect between that 2 ester through carbon-carbon bond formation. Okay, that carbon-carbon bond formation. Okay, so it is here lah. Okay, between that carbon. Okay. I highlight it using green color. Okay. So what you see here, you see the OR group that attached to your carbonyl in ester red color now no more in the structure of product. Okay, because that group is your leaving group. At the end, you will remove OR minus and it will combine with hydrogen to produce alcohol. Okay. Okay, so that's the general equation for the Claisen. Okay, for the mechanism, I think, okay, you can try by yourself. Okay, like before, same concept. The first thing, you must produce carbon ion and enolate. So after you produce carbon ion enolate, then you react with the second molecule of ester. Okay, and then you proceed lah until you get the end product. Yeah, until you remove the living group. Yeah, okay, until you get the product. Okay, you try by yourself. Yeah. Okay, so you have this empty space actually, that slide. Okay, so this one is your job to write the mechanism. Yeah. Okay, so maybe I can give the equation lah for you to write a mechanism. Okay, this is your task. Yeah. Let's say I react this one. OCH3, the first step, NaOCH3. Okay, and then second step is H plus acid, HCl. Okay, so your job to write the mechanism. Yeah. Okay, same like before. I already show you for aldol. I already show you for Michael. More or less it's look like that. Yeah, you try it. Okay, so we go to the last reaction, okay, under this topic, and the last reaction for your CHN32O2 this semester. Okay. Okay, so the last one we call it Wittig reaction. Okay. Okay, so Wittig reaction, okay, it is reaction between aldehyde or ketone with phosphonium elite. Okay, aldehyde or ketone. Okay, if you refer to this equation, okay, so your aldehyde or ketone blue color. So let's say here I'm using ketone structure. Okay, so the phosphonium elite, this pink structure. Okay, triphenyl phosphate. Okay, you have pH in the bracket 3. You have triphenyl. pH is phenyl group. P for phosphorus. And then you have double bond P with carbon. And then the rest group. Okay, R group. Okay, so this one is phosphonium elite. Elite, the characteristic is P double bond with carbon. Okay, that's the characteristic. Okay, P double bond with carbon. So the product from this Wittig reaction, it will produce alkene compound, and this byproduct triphenyl phosphine. Okay, triphenyl phosphine oxide. Okay, this is the byproduct. Okay, so this is the alkene. Okay, okay, so that's the general equation. Okay, so very simple actually. Okay, if you refer to the color that I use in my equation, my carbonyl compound blue color, elite pink color. At the end in the structure of product, you can see we combine it together. So through the double bond, okay, through the double bond. So actually, the new carbon-carbon bond formation, it's here. Between your carbonyl compound, ketone or aldehyde, blue color, and your carbon fragment in the elite structure. So CHR, actually the CHR. Okay, the group that bonded to your phosphorus. Yeah. Okay, so let's say, example. Okay, straight away. From the color, you can draw the structure of product. Okay, so let's say I have this compound here. Okay, so let's say this ketone. Okay, so doesn't matter lah. So I react it with PH3P elite. So let's say I have CH, CH2, CH3. What is the structure of product? Yeah. So straight away, you look to that. Okay, what you see here? You see this P double bond C. So this is elite. We call it as a phosphonium elite. And then you see ketone compound. Okay. So of course, this is reaction under enolate topic. Okay, under enolate topic. So actually your enolate here lah, yeah. Okay, I will show you the mechanism after this. So you will see where is your enolate here. Okay, so if you base on my equation, so very straightforward actually. So you see ketone connected to the alkyl group, okay, from your elite. So if you base on that, you can draw the structure of product. Okay, simply you just draw your ketone fragment first. Okay, this double bond, and then continue with CH, CH2, CH3. Straightforward, like that. Without the mechanism, you can draw the structure of product. You connected two structure, okay, between carbon and carbon from each compound. Yeah. Okay, so this is the Wittig reaction. Okay, so the mechanism, okay. What time now? Okay, so I still have time, yeah. Okay, so whatever it is, yeah, you need to know first, okay, the formation of elite, phosphonium elite. So actually in organic chemistry, we have different elite, yeah. This is elite based on the phosphorus. We have elite based on the sulfur, yeah. Okay, that one is not included in your syllabus lah, yeah. Okay, so what you need to know, first thing is the formation of elite. Yeah. So this elite, you can prepare it from triphenylphosphine, PH phenyl, you have triphenyl, P is phosphorus, so we call it triphenylphosphine. You react it first, okay, with alkyl halide. I just put general equation, yeah. Okay, and then proceed with the second step, react with butyl lithium, okay, Bu, butyl, 4 carbon, and then Li lithium, butyl lithium. So what you will get, you have triphenylphosphine bonded, triphenyl group bonded to phosphorus. You will get structure like this lah. Okay. Get the general equation. So the mechanism, if I draw it, you have phenyl, 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 and then that one, yeah, you have lone pair on phosphorus. So you react it with alkyl halide. Okay, so because my equation here just general, so I'm using the general alkyl halide. Okay, I have RCH2X. Okay, so what will be happen? Mechanism, phosphorus donate electron to this carbon, cleave this bond, give electron to X. So what you have? So you have PH, P, PH. You have 3 phenyl bonded to phosphorus. And then phosphorus donate electron, meaning it's produced new covalent bond with the other carbon. H, H, R. Okay, that's the first step. Yeah. Okay, so and then proceed with the second step. You react with butyl lithium. Okay, so I want to write it. Okay, Li positive charge, butyl, the carbon, okay, next to the lithium is negative charge. Okay, so what will be happen? This is base actually. Butyl lithium is base, yeah, the property. Okay, so base, as you learn, it will abstract proton, cleave this bond. Okay, so what you get? PH, P, PH, PH, and then C, H, R, negative charge. Okay. So this is actually your carbanion. So actually your carbanion is your elite. Okay. So and then, okay, I forgot. I have something. So actually this one is positive charge, yeah? Because this is neutral phosphorus, 3 covalent bond with 1 lone pair. Because phosphorus already donate that lone pair to carbon. So normal lone pair, it produces 4 covalent bonds. So abnormal number, it's carry formal charge, which is positive 1. Sorry, I forgot. So you have this phosphorus positive charge. Yeah. Okay, so this is your carbon ion. So actually, this carbon ion, or actually that one is a phosphorus elite, we call it. Yeah. Because actually simply, this carbon can donate electron to here to neutralize the positive charge on phosphorus. So you can get equivalent structure pH, P, pH, pH, double bond, CH, R. Okay, so this one is carbon ion. So this one is elite. Okay, equivalent structure, because simply your carbon negative charge can donate electron to here, okay, to stabilize the positive charge on phosphorus. Yeah. Okay, so this is the formation of elite. Okay, you should know also this one. Okay, so and then the last thing, okay, I just want to show you the mechanism for the Wittig reaction. This one, the mechanism for formation of elite. Okay, so it's not yet the Wittig reaction. Okay, so the last thing, okay, so mechanism for Wittig reaction. So I need to go down. Okay, so the last thing, okay, for the Wittig reaction. Okay, okay, so let's say, okay, so let's say I have this carbonyl compound, your ketone. You react it, let's say, with PH3P CHR. Okay, so what will be happen? Okay, the mechanism. After you produce Wittig, so then you continue, after you produce elite, then you use that elite to react with your carbonyl compound. Your carbonyl compound, it can be ketone or aldehyde. So my example here is ketone. So I already produced this elite, right, before this. So now I want to react this elite with ketone. So this reaction here, we call it Wittig reaction. Okay. So what will be happen here, okay, for the mechanism, as usual, you need to show electron flow using curved arrow. Okay, you can use this phosphorus double bond with carbon, or you can use the carbon negative charge structure. Doesn't matter which one you choose. This one. You can choose, okay, this structure or this structure. Yeah, for the reaction with your ketone or aldehyde. It's same thing actually, doesn't matter. Okay, so what will be happen here, because your elite is your carbon ion, okay, so this carbon ion actually is the nucleophile. So this nucleophile attack your carbonyl carbon, cleave the bond, give electron to oxygen. Okay, so you just draw back lah the structure from there, okay, from that arrow. So starting from the left, ketone, so you have this one, O minus. Continue with the elite structure. So you have P, PH3, and then you have methyl. It's not methyl, okay, down there. So I have R lah, yeah, I put R. Because I have R in my elite structure, okay. Okay, so that's what you see, and then so here is positive charge on the phosphorus. Yeah, so because now is phosphorus with 4 covalent bond. So this one, if I'm using this one, so phosphorus 1, 2, 3, 4, 5 covalent bond. So it's neutral, phosphorus with 5 covalent bond, or phosphorus neutral with 3 covalent bond. So if phosphorus form 4 covalent bond, it's carry positive charge. Yeah. Okay, so this is the process. Okay, what you will get here, in the same structure, you have O negative charge and phosphorus positive charge. This structure, we call it butane. Yeah, so that structure, we call it butane. So what will be happen here? Because you have negative charge on this structure, so your oxygen tend to donate electron to phosphorus. It's tend to donate electron to your phosphorus. So what will be happen? So it will produce, if I draw it, oxygen, donate electron to phosphorus, meaning you produce a new bond between oxygen and phosphorus. So you have pH3 like that. So and then continue the rest, you have this. Okay. So this is characteristic for Wittig. You must produce butane and then you must produce this one. Four-membered ring intermediate. Four-membered ring intermediate. Okay. One, oxygen, two, phosphorus, three, carbon, and fourth, carbon. So four-membered ring. Okay, so this one is the intermediate. So and then the last thing happen here, spontaneous decomposition. Spontaneous decomposition. This is very easy to happen. That's why we call it spontaneous. Yeah, because it's driven by formation double bond between oxygen and phosphorus. Okay, how it's happened? It's driven by this. It's driven by the formation of double bond between oxygen and phosphorus. Because phosphorus, it very, very stable. It is formed double bond with oxygen. So it's look like that. So what you get there, you will get N structure here. You have methyl. So and then you have that double bond. And then you have R. Okay, so that's the alkene product. Okay, so that's happened here. Okay, plus, okay, as I said, it's driven by, so you have that one, O double bond P, PH3. It's driven by this, the spontaneous decomposition. Because this P double bond O very, very, very stable. Okay, so your product here is alkene. Okay, yeah? Is it okay, student?
Yes, Doctor.
Okay. Okay, so we done, yeah? We finish. So we cover all the syllabus for CHM 3201. Okay? Meaning, today is our last lecture. Okay? Today is our last lecture. Okay? But for next week, so we still have 3 hours, right? Okay, I will use 1 hour next week on Tuesday for the second quiz. Okay, so no more lecture next week. So I will use 1 hour on Tuesday for your second quiz. Okay, and then on Thursday, free. Okay, you don't have anything. Okay, so only 1 hour on Tuesday. So actually your quiz only need around 15 to 20 minutes lah. Yeah? Okay, so quiz, okay, so everything online, yeah, like first quiz, okay, you do it in Putra Blast. Yeah, so the detail about the quiz, you just read your Putra Blast lah. Yeah. Okay, student.
Okay, Doctor.
Okay, okay. So meaning this week also last week we meet lah, yeah. Today last for the lecture and tomorrow last for the lab. Okay, so and then we meet again on the final exam. Okay, students. So see you around until our final exam. So good luck, yeah. So please study. Yeah, anything, okay, please email me. Okay, so through email or you can use message in Putra Blast. Yeah, doesn't matter. Okay, if you have question, you want to ask me. Yeah, okay, student.
Okay,
Okay,
Doctor.
Okay, thank you for this semester.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Welcome. Welcome, Shai.
Assalamualaikum.
Thank you,
Welcome,
Doctor.
Putri. Welcome.
Bye, Doktor.
Bye. Okay.